The next talk is on meta-learning for low-resource NLU tasks by Doge.
Hi, welcome to my presentation. So today I'm going to talk about our work investigating meta-learning algorithms for low-resource natural language understanding tasks. I'm Doge from Carnegie Mellon University. This is joint work with Keyi Yu and Antonios Anastasopoulos. So first, let me give a brief introduction. So deep neural networks have proven to be successful in a lot of fields, but they require large amounts of annotated data. And in low-resource scenarios, its advantages over traditional statistical methods may diminish. But in reality, large amounts of labeled data do not always exist. So we want to develop ways to tackle the scarcity of fully annotated data. And previously, researchers have tried to use transfer learning to solve this problem. So the basic idea is that they first train the model on a related task, and then they fine-tune the model on the target task. The representative will include the context vector method proposed by McCann and others, and the MAML model proposed by Peters and others. Researchers have also tried to use active learning. So the basic idea is that they want to select representative or informative examples for labeling, and the goal here is to reach certain level of performance with minimal amounts of data. And there are also some other work on distance supervision and other areas such as self-supervision. And here, in this paper, we try to do fast adaptation by learning robust and general text representations. And previously, researchers have tried to use language model pre-training, such as the BERT model, or multitask learning, such as the MTDN model proposed by Liu and others this year. In this, different from the previous papers, in this paper, we try to use meta-learning to solve the problem. So meta-learning, or learning to learn, tries to tackle the problem of fast adaptation on new training data. It covers a variety of algorithms, and here we just focus on the optimization-based meta-learning algorithms, and we adapt them to natural language understanding tasks. So basically, we first adopt language model pre-training techniques to learn high-level text representations of text, and then we continue to learn robust representations using meta-learning algorithms. And here's our training procedure. It can be divided into 3 stages. In the first stage, we pre-train the model parameters with unlabeled data sets, and here we just take the BERT model, the pre-trained BERT model, and then we use meta-learning algorithms such as model-agnostic meta-learning algorithm MAML and its variants to meta-learn the model parameters. And at last, we fine-tune the parameters on the target task. So next, I will illustrate the second stage, the meta-learning stage, in detail. So at the meta-learning stage, first, we sample a batch of tasks, TI, from a predefined task distributions. And for each TI, we compute the adaptive parameters theta k sub I with gradient descent. Specifically, for each task, we do an inner loop update. We perform gradient descent k times to obtain the adaptive parameters. And after we obtain these adaptive parameters, we use them to do a so-called meta update step and update the original parameter theta to a new parameter theta prime. And the meta-learning algorithms we use in this paper just differ in the meta update step. So next, I will illustrate this step. So the first model we try is the MAML method, the model agnostic meta-learning proposed by Finn and others in 2017. And here is its objective function. And to update the model, we just directly compute the derivative of this loss function with respect to the original model parameter theta, and we do the update. Specifically, as we have mentioned before, first we do an inner loop update to update the original model parameter theta to theta k sub I. And then we sample a batch of examples from the data set, and we compute the loss with these examples and the adaptive parameters, model parameters. And after that, we compute the derivative of this loss with respect to the model parameter theta, and obtain its gradient. And we use this gradient to do the update, to update the parameter theta. So that's the MAML algorithm. It should be noted that this step involves computing second-order derivatives. And computing second-order derivatives can be both computationally and memory-intensive. So in the MAML paper, the authors propose a first-order approximation to that. So it's called the first-order MAML, and the first few steps of this algorithm are the same with the MAML. So again, we obtain the adaptive parameters, and we sample a batch of examples from the dataset, compute the loss. But the difference is that instead of compute the derivative with respect to the original parameter theta, here we compute the derivative with respect to the adaptive parameters theta k sub I. And so in this way, we don't need to compute the second-order derivatives. And we obtain the gradient here, and we use this gradient to update the original model parameter theta. So that's the first-order MAML algorithm. And the third meta-learning algorithm we try is the Reptile algorithm. It is proposed by Nicole and others in 2018. So it's another first-order algorithm, and the idea of this is quite simple. So again, after we obtain these adaptive parameters, we compute the difference of these adaptive parameters with the original parameter theta. And then we average these differences together to obtain the update direction for the original model parameter theta. So we can see that this is similar to joint training. And if k equals 1, that is, we just do one step gradient descent for each task. This is identical to joint training. So here's a review of our training procedure. So first, we pre-train the model parameters with unlabeled data set, and here we take the pre-trained BERT model. And next, we use MAML, first-order MAML or Reptile to meta-learn the parameters. And at last, we fine-tune the parameters, the model parameters on the target task. And we perform experiments on both the glue benchmark and the Citel dataset. And for the glue datasets, we treat the four low-resource tasks as our target tasks, and the other 4 tasks as our auxiliary tasks. And we compared our method with the BERT-based model as well as a multitask learning baseline, the MTDN-based model proposed by Liu and others. So here's our results on the glue dataset. And we can see that generally the meta-learning algorithms achieve better performance than the other baselines. And the Reptile algorithm can perform better than MAML and first-order MAML. And we also try to adapt the model to a completely new task, which is the task that is never seen in during the meta-learning stage. And we can see that the meta-learning algorithm, and here we use the Reptile algorithm, can outperform the multitask learning baseline and the BERT with the same amounts of training data. So we can conclude that the meta-learning representations can be adapted to new tasks more efficiently compared with other baselines. So in conclusion, first, in this paper, we adapt 3 optimization-based meta-learning algorithms to natural language understanding tasks. We show that the meta-learning representations can be adapted to new tasks more efficiently than other baselines. In the future, we want to take the performance of the adaptive parameters into consideration during the meta-learning stage. Okay, thank you for your attention. I'm happy to take questions.
Time for one question. Yes.
Hi, thanks for the amazing talk. Could you give us a sense of like how different the different tasks in the train and dev set are? Like, would you expect this to work with like very dissimilar tasks, or does it work when the tasks are like all relatively closely related?
So for the training and dev set, in our experience, they are very similar. Yeah, and I'm not sure whether what would happen if they are dissimilar. Yeah.
Thanks.
Is the third speaker here? Okay.
Thanks.
Maybe while he sets up, maybe if there's one more question. So I had one question about. So you say if you have different number of steps of updates, as k equals 1, that can be equivalent to multitask learning, joint learning?
For the Reptile algorithm, yes.
Yes, and did you ever run with that setting?
So that would be similar to the multitask learning baseline, the MTDN baseline. So we can like outperform them. Yeah.
But you didn't run it with your implementation.
So we've tried different k in our experience, and we found that when k equals 5, it performs the best. Yeah.
Thank you.